Okay, so welcome everybody to our last talk of the semester. I'm extremely happy to have Charles-Albert Lehalle give a talk today. He's given a talk with us a few years ago about NLP, and that was, a few months or years, maybe a year before the LLM revolution that we've seen. And so he's a professor at the Ecole Polytechnique in Paris. He's has a very diverse set of research projects that he's worked on. He's also a great friend. I really enjoy his sort of philosophical outlook and take on diverse things from, LLMs to market microstructure to supply chains and many other topics. In fact, he has a yearly calendar that he publishes, and every month has a sort of a theme to it. And actually, I was looking at the 2025 theme, and April turns out to be exactly this, the sort of applications of Gen AI and generating time series and sort of the pros and cons. So I'm really excited about this talk. So the rules of the game is, if you have some questions, please put them in the Q&A. I will mostly keep them to the end, but if you have a question that requires clarification, I'll jump in. Otherwise, we have links of the paper in the chat, and we have links to our YouTube channel. So anyways, Charles, please take it away. Thanks for coming to our seminar.
Thank you for the gentle introduction and for having me a second time. And I'm not sure I can match the diversity of topics that you are addressing, Sasha. But in any case, for today, we will talk about generative AI. So I use a former template for the first slide. So we are not in Paris. We are virtually in New York, and the topic will be generative AI for financial time series and specifically for portfolio construction. And with my co-author, Jim, we decided to put as a subtitle of the paper this sentence: "A throw of the dice will never abolish chance," because it's the title of a poetry by Stéphane Mallarmé. And it was at the very vivid time of probability in Paris, where the central limit theorem has been discovered, etc. And even all artists were very puzzled by this idea that once you throw the dice, does the uncertainty and the randomness persist, or did you solve it forever? And it is indeed the topic of generative AI. It is how can you reproduce the randomness of something without killing it and reducing it to a subset. And we will today go through this diagram diverse ways. And so let me explain you the different concepts that I put on it. So we've got a true process that generate financial returns of financial instruments, equities, for instance. And we want to compute theta, that is an estimator, that is the expectation under the law that we don't know of these financial returns, for instance, of a function of them. Typically, you can think about the Sharpe ratio of a strategy. But you don't have access to all these to this true generative mechanism. You don't know how economy, how geopolitics are shaping financial returns. You just observed a few of them. This capital M, that is a sample size of X. So X are the samples that you've got access to. And so what you can do is compute a U statistic based on X, the observation, and endpoints. And somehow the quality of what you will recover, if you just apply the formula F to this X, is at a distance 1 over n or 1 over square root of n, depending if you talk about the variance or the distance of this theta. So already you are in a subset that embeds some randomness. What can you do with that to try to understand what is the true statistic of interest? Think about the Sharpe ratio of a strategy. There is a very old way to do that. That is a bootstrap. It will be the block bootstrap for a time series. So block bootstrap, this B, N is the number of available data that you cannot change, and K is this resampling. So you can resample, and you've got access to something that is around theta. Around is a sense, in the sense of the papers of Effron, for instance, who invented the bootstrap. So the confidence interval will be quite decent. The other aspect is, the other solution is to build a generative model. This phi of n, I mean phi indexed by n, because to be sure we remember that we build this generative model only with n points. And so you've got a u hat n, that is the expectation. Now you could have access to the true theoretical law of this new x via your generative model. What I'm saying here is that, of course, we will throw a very large sample. We will of size capital M, that is far larger than n, using this generative model. But before that, now that you freeze the parameters of the generative model, there is a law according to that. If you randomly sample an infinite number of synthetic data, you will have access to the true expectation. So it exists, and it is close to what? It is close indeed to this UN. It is not close to theta. It is close to UN. And then you will throw as many samples that you want. And this X tilde, for instance, and the more sample you will synthesize, the closer to this one you will be. Throwing a lot of, randomly synthesizing a lot of data will get you close to this one. And so we will explore how far from this one you will be. That is the first part of this talk. The second part of the talk will be, okay, as I said, you will try to use that to fine-tune the hyperparameter of an investment strategy. Let's say a portfolio. You will build a portfolio using your favorite algorithm. Can be sophisticated or not. And you will try to assess the hyperparameter of this algorithm using your synthetic data. And what you will do at the end of the day is something to control the risk. And your risk control layer will be close to the Markowitz approach. It will be probably more sophisticated, but indeed, you will go towards maximizing expected returns, so mu, on your portfolio. W are the weights. It's a vector with the weights of each line in your portfolio. Mu is the expected return that you computed. And W transpose omega W, omega being the covariance, will have to be maintained under a given level of variance, of risk. So you will do this kind of computation. And we will see, it will be the second part of the talk, in 2 slides, I think, or 3 slides. We will see that generative models are very, very bad in providing data to solve this problem. That's something that, that we will clearly explain. But this paper that I'm relying on is not the only one trying to provide synthetic data, ways to build synthetic data in finance. Here we reviewed all of them, so we'll have far more detail in the paper. And but you see that there is also something that is important to note, or at least it was for me very impressive to see the diversity of the instruments that have been used, the historical period that have been used, the metrics that are very diverse, and most of the metrics are indeed, during the learning process, do we make progress? But it's not in terms of, I don't know, the Sharpe ratio of something, is it better than another method? In machine learning, the good practice is to measure yourself, to compare yourself to other algorithms, and nobody is doing that. And the metrics themselves are very diverse and very difficult to compare. And even something even stranger, I would say, is that there is, in most of this paper, there is no out-of-sample test. No out-of-sample data. Most of these paper, there is no out-of-sample test, and there is only visual check. Does the curve of the trajectory, the time series, look like time series? That personally, I don't know how to do. So if you remove all of them, all the ones that have no out-of-sample and at least one quantitative measurement, you end up with 3 papers only. So I think that what is important also, and it will be in the conclusion of my talk, is to try to structure the community that is researching on synthetic data in finance to be able to do the same progress that people did in machine learning, in vision especially, and then in language models, having benchmark data sets, having benchmark problems to compare. Because you may know the no freelance theorem in machine learning that says that there is no universal algorithm to solve all the problems. And so we learn that this proposal is better on this kind of statistics or analytics, this other kind of analytics. And practitioners will be able to combine these proposals to make something that suits to their needs. So this paper is also a call for more comparison and more unification. So as I said, this aspect of some small sample size, portfolio construction, and then we will also make a proposal of architecture, and that is for me not the main point of this paper, but it allows to make an illustrative exercise of comparison. Okay, so small sample size. So there is something that took time for me to understand this slide, to be able to produce this slide. Indeed, even I have been able to understand that after we finished the paper. We first finished the paper, and then I realized, discussing with different people, especially Michael Jordan, was a very interesting paper. This one with Angelopoulos. To understand the link of what we do with things that people were doing for long. And I will start by the second formula, that is the one in Michael Jordan's paper, because in machine learning, they discovered that synthetic data are not providing good confidence intervals, and even they have a bias. And so in this paper that I'm citing here, they take example of generating molecules, generating weather data, etc., and showing that there is a bias if you use the standard synthetic GANs or generative models. And they propose a way to correct it, and we will see what it is. Then before that, I realized also very recently that indeed generative, considering properly for statisticians, generative model is exactly like missing values. What you have to understand is that what is the missing value when you want to do a generative model? Remember how it works. A generative model that starts from a normal distribution, generally a Gaussian distribution, and project it, transform it in a distribution that is close to your initial distribution, the one you want to synthesize. And so the omega that are drawn according to a Gaussian are always known. The unknown variable is X, what you reproduce. So you can imagine that when you will generate synthetic data, you've got 10% of your data set with omega and X. So the randomness seed and your example, maybe 100 couples like that. And then you don't have any examples, any financial time series, but you have a lot of Gaussian random noise that are indeed random variables, and you will map them on your synthetic data that will be a replacement. So this is data imputation. And so you can use all the results, you could use all the results of data imputation to understand synthetic data. And it will be very valuable if you want to mix historical data and synthetic data, because all the setup is there. But in the 90s, statisticians understood that data imputation does not work. It's not the best way to produce to replace missing points. It is a very old way to do data imputation. So what is data imputation? Is that you produce a model to replace missing data. That is not the optimal way, and from far. The optimal way is incorporates more randomness, closer to bootstrap indeed. So there is this paper by Effron explaining part of it, but synthetic data is typically data imputation. So you will recover the result of data imputation. So pre-90s, if you want to understand how to mix real historical data and synthetic data. If you remove 100% of your historical data, you only rely on synthetic data. You cannot reuse the traditional result of missing data because you will have somewhere 1/0. You've got zero reuse of data. But recently, in this paper, Michael Jordan and his co-authors proposed a formula that obtained better confidence intervals. And so remember that in my notation, X tilde is the synthetic data and X are the original data. And usually, for instance, this is the example if you want to produce simply the average on your sample. So 1/m, I mean, M is the number of synthetic data you produce, and N is the number of historical data you had. And so the old way is to say, okay, I have my synthetic model. I am able to produce as much X tilde as I want. So let's say capital M, very large. And I will just use the average over these points. And my confidence intervals will be part of the 1/m will be part of the confidence interval. It's not how it works. Indeed, to have correct confidence intervals and no bias, you need to have this corrector. That is 1/n, that is 1/n times the difference between the historical data and the synthetic data corresponding to this historical data. That is the out-of-sample error. What this paper and this result simply means is that you cannot do better than the out-of-sample error. Okay. So, and that is in the spirit of what I will tell you now, and that's probably easier to understand, by the way, than the formulas that we will see together now. So here I tried to make a simple schema here, diagram that you've got theta, that is an unknown parameter you want to estimate. You've got only capital N data. And so if you produce the same statistic on your capital N data, you obtain UN, and UN is at the distance AN of the truth. And this distance is never zero. This distance is something, capital R, that is larger than zero, because you never are exactly at the unknown true value of this variable. Then you've got a learning process. During this learning process, you will go a little away from this UN for two reasons. First, because your mechanism of learning is not perfect. If the mechanism is perfect, you could be exactly at UN. You will never be exactly at theta because you don't know it. If you've got a lot of regularization, you will go away from UN. Regularization are constraints, and constraints, if you put them in front of your loss function, will prevent you to minimize exactly the loss function, so to be exactly there. Okay. So the regularization will pull you away, but to be able to pull you in the correct direction, it has to know the structure of theta that we don't know. So it will never be exactly at theta neither. And now you generate a lot of points UM. And these points, the statistics you will obtain by computing it on the synthetic data will be centered on U hats. And the more data you will have, the more peaked it will be, like this. Okay, it will be peaked. So we've got this UN that is somehow a Gaussian around the true parameter, and the variance depends on N, the number of initial sample size. Then during the learning, you are close to this UN. So you are inside this small ball. And then the more you decide to add synthetic data, the closer to your hat you will be. So the further away from theta. That's something that is known from the no-free-lunch theorem results in machine learning, but we can formulate it this way. You've got concentration inequalities, and you can really show that it's the case. So this B is the B of the previous time, and I've got capital, I mean, this constant A, etc. And so in the paper, you will see that this combination works, even in high dimension, for U statistics and for L statistics. Remember, that U statistics are like mean, standard deviation, Sharpe ratio, etc. And L statistics are useful in finance because the value at risk is L statistics. They are quantiles. So you can reproduce these results in high dimension for U statistics and L statistics. And so you will be stuck away from theta. That is the purpose of the no-free-lunch theorem. I remember I was doing my PhD in the 90s in machine learning, and the community has been very sad when all these theorems started to emerge, saying that, okay, without any knowledge of the truth, you will never be able to choose the correct model. And so this is a dream of trying to do that. And for these specific financial data, it's even more difficult. And the question is, how can you convince yourself now? So let's make just a remark, is that why do we think it works for images? Why do we think it works for text? First, nobody says it works for images and text because we don't have any metric to compare the true distribution in text and in images and what we see in front of us. When I ask to GPT or one of his cousins to restate my slides in the style of Stéphane Mallarmé, the poet, I have no metric to know how close it is from Stéphane Mallarmé compared to from, I don't know, another poet. So it's very difficult to assess the quality of the generative models. For molecule, it's not the same. For molecule, like AlphaFold, you can, because you can see if the generated molecule corresponds to a drug. And indeed, in Michael Jordan's paper, they show that it does not work in general. So you need to have some corrections. And for images, if you listen to the talks of Stéphane Mallat, for instance, at Collège de France, he believes that what works for images, it's because the structure of the neural nets that are used to generate images is very close to the way images are produced. It's multi-scale, it preserves some colors, and you've got this kind of objects, you've got this kind of gradient detection on the top of it. So, so it means that maybe for images, we got a little bit of regularization that works not that bad. And so this small L, during the learning, pull the generative model out of what it sees and closer to the true generative model. That is the bet you've got to do when you build a generative model. And so how convince ourselves that it will be the case in finance? It will be my last slide, the methodology, the benchmark, etc. Before that, we can go on portfolio construction. That for me is something that is very important to share with you, in the sense that a lot of people are using synthetic data of equity returns, are synthesizing equity returns to build better construction, better risk management in general. And if you look at the equations, you need to do something very, very not natural, I would say, to make it work. And all the GANs that we've seen in the literature are not doing that. So why? Say that you've got a risk model. Remember what is a risk model? A risk model will enable you to decompose the risk of a portfolio. And remember, my risk of my portfolio of weights W was W transpose omega W. It's quadratic. You've got something that is a diagonal, a matrix that you can diagonalize with principal components that are factors, usually considered as factor, a diagonal, and the transpose of these factors. And you've got a residual, let's say, idiosyncratic noise that you can decompose this way. When you do that, and now you make, you multiply an arbitrary vector that soon will be our expected returns by the inverse of this matrix, it's possible to compute exactly the result. As soon as you've got a risk model, that is why MSCI, Barra, Axioma, etc. are selling for very expensive price risk model, is that you can compute explicitly the solution. And what is the solution? You take your factors, the capital P, and you make the scalar product between your expected returns and each of the factor. This is that. The scalar product by my factor number K. This coordinate will be along my factor, pk, that is a vector. And what will be the scaling? The scaling will be in 1 over lambda k. Lambda k is the eigenvalue number k of delta, of gamma, of delta, so of this matrix. So what does it mean? It means that the portfolio construction, remember that when you do a portfolio construction, you simply multiply on the left by the inverse of the risk. And so this is the essence of a portfolio construction using expected returns Z and a risk factor omega. What you do is that you rescale the exposure, I mean, the part of your expected returns that are collinear to the factor number K by 1 over the eigenvalue associated to this number K. It means that the factors with high eigenvalues will be reduced to almost 0. So the exposure, so if you've got a wonderful predictor that predicts in the direction of the S&P, it will be completely removed by a portfolio construction. If on the opposite, you've got signals that enables you to predict returns in a collinear way in the last principal components of a PCA of the covariance, they will be preserved. So now that, so this is simply this formula. Now that we know that, what is the kind of returns that you need to be able to synthesize to use for portfolio construction? The ones that are far away from the largest eigenvalues. You need to be accurate in the small eigenvalues, because it is where the portfolio construction will drive you. The portfolio construction will align your portfolio with the small eigenvalues, small eigenvectors associated with small eigenvalues. And so you need to be able to produce synthetic data in this direction. Unfortunately, most of the, I don't need this one, most of the GANs are not doing that. Okay, most of the GANs are aligning the synthetic data with the component of large variance. If you think about the Wasserstein distance, and for instance, so in the paper, we've got more accurate proofs, but here I just take one example to give you the sketch of what is happening. If you compute the Wasserstein distance, that is the distance that is used by a GAN to measure how well it fits the distribution of returns you want to reproduce and to synthesize. And if your returns are Gaussian, the distance between those two, the synthetic data and the historical data, will simply be a formula involving the variance. And you can show that what will drive your GAN, the accuracy of your GAN, are the large eigenvalues. So if you keep a standard GAN using Wasserstein distance, it will focus the parameters of the generative model where it's less useful for portfolio construction. It will preserve the noise and the bad prediction, the bad synthetic data. It will keep them for the components with low variance that are the one you need. Okay. And so in the paper, for instance, we could prove a theorem like that. If you perturbate your factor by epsilon. That is what the GAN will do. And now you consider two GANs, one that perturbate the first eigenvalue and the other that the second eigenvalue and the other that perturbates the last eigenvalue, for instance. The error that you will obtain on the portfolio construction will be far larger if by the one that focuses attention of the large eigenvalues. So it means that the GANs we are using to produce synthetic data in finance are producing meaningful data where we don't need and noise where we don't need, where we do need information or autocorrelation or cross-correlation. So all the value that you can expect for synthetic data should be located in the small eigenvalues. So, but it's not completely lost. You've got solutions. So what did you learn up to today? We learned that so it's difficult to get confidence interval with you start with a small sample. It's good to check if your model is identifiable, meaning that if your model reproduce some structural properties of the underlying model. And what we just saw is that you need your loss function to be focused in the principal space. The principal space in the space once you cleaned from the large eigenvalues. So it's not very difficult. You take your returns, you make the PCA of their covariance, you go in the PCS space, you multiply your discrete transformed return by 1 over the eigenvalues, and then you rotate back. And now you are in a space where the GAN will not focus on one eigenvalues instead of another. They will be all equal. So you can even invert this principle and try to put more, to remove more information on the large eigenvalues if you want. But at least you should clean them and put all of them on the equal footage. So to do that, what we did in the paper is not very difficult. It's exactly what I said. You take your original data, you do a PCA, you clean, you remove the variance. Once you made the rotation of the PCA, you remove the variance and you rotate again. And now you are in a space where, or you stay, I think we stayed, in this rotated space. And now you've got if it was a S&P 500, you have 500 time series that are cleaned all on an equal footing in terms of variance. Because as I said, we've got this small sample problem. You don't want to do to make a big GAN for 500 dimensions. So what you can do, and what we propose is that you cluster these trajectories that look like similar. Now that you've got 500 trajectories that are cleaned from the variance, you've got far more that are similar. So here we took 3 GANs, 3 clusters, and now you only have 3 clusters for 500 time series. So you've got far more points per GAN, 3 GANs. So you do your best to try to counter the problems that can be proven mathematically. They are very important problems. Small size and this covariance problem. This variance problem. So we did that on a subsample of the S&P 500. We had access to how much? 40 years of data. So we took the 12th first year to do the GAN and the 2 remaining years to compare, to have out of sample. So what I show you here, so that's another point that I think is important. What I told you at the beginning is that we need benchmarks. So here, the S&P 500 is a very simple benchmark. I think it's good to take it, but you've got Russell 1000, you've got some European indices that you could take also, etc. But on one, how can you think about something that is like publicly documented and concerned like a signature of the returns of financial instruments on equities. I think the mean reversion signal is a very good candidate. Because the mean reversion signal, so you've got the initial paper by Avellaneda that is very clear mathematically, and then Georges Papanicolaou did another version of it later, 7 years later, and the mean reversion signal works pretty well if you don't take the friction cost into account. What is this mean reversion? It's very simple. Huh? You play the mean reversion around the factors of the PCA of and so the ones that went away, you bet that they will come back because you believe in the stationarity of this distance between the PCA, between your returns and the PCA. And it works in the sense that the Sharpe ratio is positive at up to 1 week. That is documented academically. So here I have my the size of my window. You see that up to 1 week and even a little more, the Sharpe ratio is positive. Huh? 0 is here, the Sharpe ratio is positive. And if you increase the window, so you've got a lower and lower Sharpe ratio, and it's very natural because we know that the momentum signal exists. Huh? This is this paper. There are a lot of papers documenting the equity momentum. What is equity momentum? Is that you bet that the stocks that overperformed will continue, and the one that underperformed will continue. It's exactly the opposite of mean reversion. And the time scale is 1 year. Okay. So when you go from 1 week to 1 year, the Sharpe ratio goes from the positive domain to the negative domain. And if you go at the level of 5 years, it's documented by macroeconomists, you go back in the domain of positive Sharpe ratios. So this signature is, I think, something we could check each time someone is building a GAN to produce synthetic financial returns for equities. Just do this graph. Do your synthetic returns reproduce the fact that you start in the positive realm up to 1 month, or even 2 weeks, something like that, then goes into the negative realms, and then go back. So here we didn't have enough data because this one is in sample. Huh? It's block bootstrap that produces the confidence intervals. The in-sample data are here, these black dots, this black line. And the red is out of sample. Remember, out of sample is only 2 years, so it's natural that is noisy. Nevertheless, it's good to keep out of sample and to look at it. So now, what happens if we use our GAN to reproduce the same chart? Where is it? Here. So this is the chart that we just saw. And on the right-hand side, you've got the one using the market generator, synthetic data. So now, the box plots come from the market generator, the synthetic data. What to say? So it's expected that it's no more centered on the historical data because you get a lot of regularization, and so it pulls you away. So this one is my UN. UN in my initial slide is this line. This is the one you can measure on your in-sample data. And of course, the bootstrap, it's centered on that. Huh? There is no other way. But here it's not centered. And you see that, okay, in this region, you are not that bad. You are compatible with the out of sample. But in the rest, it's not very good. Huh? So what can you do? What can you do to give you an idea of how far away you are from the truth? There is something that is feasible that in statistics is called identifiability. And my PhD advisor was always telling me that I should do that when I do a machine learning model. What does it mean? It means that you take one instance of your model. So the GAN that I've shown you that we are using, you take one instance of it. You produce data with this instance. And now you feed another GAN with this data. We call that a regurgitative model, because there are papers calling that regurgitative learning. So why is it good? It's good because now you know the truth. The truth is your initial GAN. So how much are you able to recover the properties of the truth, that is the one of your GAN, with another GAN of the same class? Frankly, if you can't, just stop using this GAN for financial data. So what we did is that we took this GAN, the one that we trained on the historical data. And now we believe we make as if it's our own truth. Huh? And we can play a little bit with it before learning something on it. What is the kind of thing we can do? You can ask to this GAN, now you know the ground truth, the true expectation of the signature of the Sharpe ratios across scales. This is this green line. It means that if I have access to an infinite sample of my synthetic data, I will get that. And look, to be able to make the difference, even at 1 week, that we know that at 1 week, the mean reversion should work, should be positive. The Sharpe ratio should be positive. To keep it positive, you need 120 years of data. Now we know that because we know all the statistics. It means that for this class of GAN, to be able to recover a simple, property of the mean reversion, very documented by academics, you need at least 120 years of data. And we just had 12 years, okay? 12 years, it is this gray zone. Huh? So you can expect that the GAN will go somewhere in this gray zone. So here, what did we do? Now you can try to play with your comparison. But it's good to make this statistic because you know the ground truth. It's a fake truth, but it's a truth. It will be the one for the purpose of the exercise. And we randomly choose one sample. Okay, remember that the true expectation is this green line, and by lack of chance, we got these dotted points. It's not exactly the same, but it's a game. Now, 12 years of data, like the historical period we had, and we will learn a new GAN, or regurgitative GAN, will be learned on these dots. What is it able to do? Okay. So remember the green line is the ground truth. Okay. And now, so here on the left-hand side, it's block bootstrap, and on the right-hand side, it's another GAN of the same family that learns on this data line that you've seen. It was away from the green. But this secondary GAN, the regurgitative one, he never saw the green line. Nevertheless, look how it could recover part of it. So it is pulling the models, the parameters in a good direction somehow. Huh? It is closer, the confidence interval we have is closer to the green light. The green line is closer to the center of our confidence interval than the one here. So it means a lot. It means that our GAN is able to learn the intrinsic structure of a GAN of its kind. I'm not saying that the market is like that. Huh? I'm saying that at least there is a consistency somewhere. And it is doing that better on the short time scale. That is probably due to the fact that this GAN has a memory that is not infinite. So it's easier for this GAN to understand what is happening on small time scales. So already doing this sanity check is very valuable. Okay. And now we can go to the conclusion. What did we do for that? We learned in the principal space, this idea of doing a PCA, putting all the time series on the same foot in terms of variance and learning on them that are meant to be independent, by the way, statistically independent, conditionally to the PCA. Then I think it's very important to have stylized fact that you want to check. Here we said, okay, it will be the mean reversion, but it was an academic exercise. Maybe what you want to do is to have a portfolio that is more robust to value at risk. So you want to do an optimization with a gradient descent to minimize the value at risk of your portfolio. By the way, I started this paper with Renjim, my co-author, because he has a very nice paper on using gradient descent to learn to protect portfolios against value at risk, bad value at risk. So you can have your own operational criteria, and I think it's very good to include them. In one of the papers that remains from the long review that we've done, one by Ramaconte stayed in the second list, and it was probably because Ramaconte and his co-authors, they were focusing on specific properties that they wanted in terms of model risk, etc. That is a very important point, an anchor that you can use to try to not hallucinate somehow. Huh? And then you probably should investigate the identifiability of the model with this kind of regurgitative approach. You should always use block bootstrap because we know that it's impossible to do better than block bootstrap with the points we have in terms of confidence intervals. I mean, without adding structural assumptions. And then we need benchmark problems. And I propose that this mean reversion signature could be one of our benchmarks to measure where a given GAN is good or not in terms of memory and that. And that's it for the talk. So I'm ready for the questions. By the way, this image has been, of course, produced by an image generator than an AI. With the introduction of the paper.
So what was the prompt? You gave it the entire paper, or
I gave the introduction, the first paragraph of the paper.
And the formulas came from the paper?
The formula, I added them myself.
Okay.
They come from the paper.
Okay, so you added a little bit of artistic touch there. So I don't see any questions right now in the Q&A. I'm quite curious about the first point you made when you did the literature review, which was that there's almost no two papers that look at the same data set. And that to me is like a big issue in the field. And, you know, if we compare to like machine learning, there's the movie lens data set, there's the Yelp data set. I've been looking recently at the Vivino data set. And all of these, you have multiple papers written about it, and there can be a debate, you know, my model is better than your model. But and you know, to be fair, like this literature also has issues with agreeing on what a good metric is, and you know, maybe maybe that's common to all science in a way, but the fact that the time periods and the instruments are so sort of all over the place makes it hard. So what do you think is you know, the cause for that, or why don't we have, like, let's say, you know, a famous data set that everyone looks at?
So first, you're right. In machine learning, the progress came from sharing same data sets, same metrics, and same problems, even if there is a debate. I'm not saying that, for instance, as of today, especially in image processing, there is a debate that if you go away from the benchmark data sets, you are far worse than expected. If you look at, and for LLMs, the last issue of the AI Index report by Stanford University that is a huge list of all the benchmarks, they are saying the same thing, is that people are competing with their LLMs on very narrow benchmarks. And especially, for instance, for math exercise, you can be good in the benchmark in math, but if I use an LLM to solve my mathematical problem, it will be very bad. So to come back to your question about why, I think there are two reasons. The first one is that there is these data are not free. So and they are very expensive. The financial data are very expensive. And we should probably, a handful of academics should go to MSCI, should go to, I don't know, Morningstar, to get a free sample of data documented with no look-ahead bias, because most of these papers have look-ahead bias, even ORS has some. So because it's very delicate with the total returns of the instruments and not just the daily returns, I mean, including the dividends, etc., the outrights. So that is very expensive to build a data set like that, and that's one of the reasons. For me, the second reason is a very bad one, is that most of the authors want to be hired by an hedge fund, and they just want to disclose something that has a good Sharpe ratio. And so they are not really interested in competition, in academic and knowledge sharing. They want to show good Sharpe ratios. And so I think that we need to, it will be also, if we do that, if we converge on a sample, on some metrics, it will also prevent to be polluted by this debate about producing and reproducibility of results in finance. That is a true problem. That is due exactly for me to the same, that the data are very expensive and people want to be hired by a hedge fund. So I think if we start to, at least for generative models, we start to have a set of reference data sets. For instance, there are, in terms of high frequency data, you've got the Lobster data set that is not too expensive. And in France, you've got a data set that is free, but stops in 2018. And that is offered by the French regulator. I'm part of the scientific committee of the French regulator. You just need to compete academically, I mean, to make a proposal to be able to get this data. That is called BEDOFI. And the Institut Louis Bachelier is now taking care of this data set for the community. So it's possible. But I think that high frequency data are not the main purpose of because frankly, high frequency data, you know that better than me. You worked a lot in this space. You already have a lot of data. Why do you want to generate synthetic data? It's useful for daily data. So
yeah. But I find that every time I write a paper, it's a little bit ad hoc. Like I'll find, oh, this came from Lobster, or another year I'll find some. So most of the papers, I guess, are a bit exploratory, and then it's kind of a bit harder to advance, consensus around, different models. So, but I mean, in some of this is S&P 500, like that stuff is, free. You can get daily data on this, but even, the fact that you had 433 and it was sort of like, there's some selection bias and there's some things that if everyone that writes a paper has to do all that work, it sort of like makes it much harder to compare, I guess. So yeah, I do think that working on our, the finance equivalent of the Netflix data set or the Movie Lens data set, that would be very helpful. Okay, so we have a few questions in the meantime that popped up. So the first one, how do you deal with short-term trading in terms of Sharpe ratio? So I'm guessing they mean, and then they say, I mean, there should be certain optimization in small windows.
I think that there are two things about that. Maybe to try to answer to this couple of questions, is that first, here the optimization in small window is the mean variance. I mean, the mean reversion is taking care of that. The mean reversion algorithm is taking care of the optimization, and so you reproduce it. So you reproduce essentially the paper of Avellaneda or the paper of Georges Papanicolaou with your data set. You can do a very simple version because now that you are in the principal space, the mean reversion is very easy. Because remember, the Avellaneda's paper on mean reversion it is stationarity around principal component. So here you are already, I mean, for us, it was easy. We were already in the principal space. So it's mean reversion inside that. And remember, there is a tau that is the mean reversion time. So he makes first a selection on the short-term mean reversion time, and then does the long-short portfolio on the top of it. But it's not very difficult to reproduce that. And if you are talking about the frictional cost, I mean the trading cost, I think it's not the purpose of the exercise. We want to see if we reproduce the stylus facts of the returns, not trying to build a portfolio that makes profits. It's another layer that people will add on the top of synthetic data.
Okay, so we have another question that talks about, sudden uncertain shocks, example, tariffs or unforeseen circumstances. How shock-proof do you think these generative models might be? Do you have to, as long as you have some shocks in the data, they'll reproduce these shocks, or what's your thought on like extreme?
So it's a very good question. I think that the answer is in the question. Indeed, there are statistical models. So you've got two ways to be able to do something that is more extrapolation. Either in your historical data, your small sample size, you've seen a few directions, at least during a few months, that went into the correct direction, in the correct perturbation that the shock will have in the future. So maybe you've got this kind of joint move of returns that can be present when you reproduce that with synthetic data. Either the second possibility is that you structure the model. So you add knowledge inside the model. You structure your GAN to be able to do things like that. There is a very nice paper by Emmanuel Gobet, for instance, where he focused on synthetic data so it's not in the list because it's not applicable there, but for value at risk construction, and he has a very clever idea or remark or observation that if you remember that most of the GANs, their seed is a Gaussian. It's a Gaussian distribution that you transform and you project. But if you want to focus on skewness, maybe you need to start with a distribution that already has some skew. So you take a fat tail distribution at the center of your GAN before producing. So there are ways, and it will produce, because remember what are doing GANs? GANs, they are neural networks, deep neural networks, with an input that is a Gaussian, the usual GANs. So what is a neural network? Think about a ReLU. A ReLU neural networks, it makes simply a lot of truncated linear combinations of the inputs. So what you will have at the end is a very long linear combination. Guess what? Linear combinations of independent noise, due to the central limit theorem, they will be Gaussian. Okay. And if worse than that, you start with a Gaussian and you got a lot of layers, sure, you will end up with something that is Gaussian, but not a lot of skew. It will be difficult to introduce skew. So if really you are focused on the skew for VAR, value at risk, maybe you should start not by a Gaussian, but by a fat tail distribution. It's a very nice idea.
Someone is asking if you have like a conclusion on the question, comparing Bootstrap versus GAN, which one captures more information of the original series?
Okay, it's a very good question. Where is it? I lost one slide. Where is it? Ah, no, this is one. So I'm a very big fan of Bootstrap. So it will be difficult to convince me that you can do better than Bootstrap. At least bootstrapped confidence intervals, we know what they mean, and we know that they are correct in a sense. But look at this correction proposed by Michael Jordan and his co-authors. Okay. So you want to compute the average. So it works with the variance of that, of course. You want to compute the average. You've got your synthetic data. And here, you've got something that is the out-of-sample quality of your synthetic data. Your out-of-sample quality, because you want to estimate the average, it's 1/n. It means that the only way to reduce that is to be good out of sample. So somehow if you capture, so it's not very important, I mean, it's not very important, it's not needed to have a very large sample size if you have a very small out-of-sample error. And once you've got a very small out-of-sample error, now you can afford to produce a lot of data with your synthetic generator because the 1/n will work. If you are far away out of sample, then you can produce as much data as you want. You will reduce that to 0 in terms of variance and confidence intervals, but it will remain. You will stay, and what will it be? Something like the bootstrap. So you will never be better than the bootstrap because it's non-parametric. And if you make an error on out-of-sample error, you will never be able to do better than the bootstrap. If now you've got a very small out-of-sample error, you can probably go further than the bootstrap. And it's more or less, maybe you should read this paper by Michael Jordan. The title is Prediction Powered Inference or something like that. And you will see the different components working together or not. And so probably it's feasible to go further than bootstrap if you convince yourself that what you capture out of sample is really out of sample. That is always a difficulty.
Okay, so I guess we do have a last one that I'm going to mention. Is there any work being done on power law distributed synthetic data generators, not just GANs, that you know of?
There is this paper by Emmanuel Gobet that is close to that. And it comes from what I said, that it's very difficult because officially, the central limit theorem will tell you that if you use a very deep, I mean, it will be very difficult with a deep ReLU neural net to do not reshape any distribution in a Gaussian. So the learning will have to be very powerful and we'll have to resist to this. And because initially, when you will randomize the weights of your neural net or initialize them according to a PCA or something like that, it will be very close to a Gaussian, the output, even if the input, the noise, the seed noise is not Gaussian, simply because of the central limit theorem. But to fight against that, you need to inject in the seed, so the omega here, Pareto, for instance, and you need to do some early stopping as regularization. There is a very nice paper, I think, called Early Stopping as Regularization that will tell you how to do that, and so it will be a good regularization for that, in the sense that you will not mix too much the data or massage too much the data that will reshape them in a Gaussian.
Okay, well, let's leave it at that. Thank you so much for speaking at our seminar, and I hope you have a great day surfing in the south of France.
Thank you, Sacha, and thank you again for the invitation to having me. Bye.